let's see exactly another way to compute this thing. So I hope this is clear because it's not so easy. So basically we have right now a tank. Let's try to use exactly name. So we have right here a turbine, and we had this pipe and a little one, okay, and another tank, which is the tank B. Alright, so another way to, so with the things that we have that we have seen in the slide, in the end we said that the total head before and after your turbines is equal to, it was Hm minus Hb, which are exactly this point and this point, and they were Y minus losses. Right now, where Y was HA minus HB, so respect a reference system, we are talking about this stuff, HA minus HB. Alright, so there's also another way to express these things, and we will see it better doing some exercises about system and the equation systems. But right now let's try to exactly impose what is called the systems equation. That basically it consists in writing Bernoulli's theorem from point A to point B. So I am the flow and I want to move from tank A to tank B. From tank A to tank B I find total head in tank A. Then, for example, we are not considering the concentrated losses. Alright, so I hope it's clear. Then we start from HA, then we have the first distributed losses from tank A to the point before your turbine. So right here you have J1 L1, so it will be HA minus J1 L1. Then you have what? The decreasing of your energy due to the presence of the turbine. So you will have minus delta HT, which is exactly what we have found before in your slide, minus delta HT, so you have a decreasing, then you have again a decreasing due to the presence of distributed losses along the pipe number 2, then you have minus J2 L2, and everything, just consider that you don't have concentrated losses, is equal to HB. Again, if I get delta HT from this thing, you will obtain delta HT equal to, I bring it on this side, so I will have HA minus HB minus G1 L1 minus J2 L2, which are, it's like to say HA minus HB, it's your Y, minus J1 L1 plus J2 L2, which are your losses. So again, you obtain exactly the same consideration. So let's go back to our slide. All right, and then we can say we are right here. Then we can, once we have found the energy associated with your turbine, we can compute the transferred power. So the available power of your flow is the specific weight of your flow times your volumetric discharge times y, which is again the available difference had from tank A to tank B. At the same time, the transfer power Pt is given by the product of the specific weight of your flow times Q times delta H, which is again the decrease of energy due to turbine. In the paper it was delta HT is the same. And the transfer power is the energy transfer from the current to the machine in the unit of time. Finally, you are able to compute the actual power, which is the power effective that needs your turbine. So it's the efficiency of the turbine, and usually it's almost 0.90 times the specific weight times the volumetric discharge times again the decrease of energy due to the presence of the turbine. Alright, so let's right now see the case of the system with the pump. So what changed? Well, it changed that in this case you want to give energy to your flow. So if you want to give energy to your flow, you need to insert a machine that is able to give this kind of energy, and this machine is called the pump. Basically, for example, if you observe this scheme, you will see that you have right here a tank which is at a lower energy level respect the second tank right there. This pipe usually in a system with pump is called the drive pipe, while this one is the delivery pipe. We will see next that there are some problems usually in the drive pipe, problem related to the cavitation of the pump, which of course are a serious problem, and they occur when the pressure before your pump is such that it can create bubbles. So you have a pressure that is almost equal to the vapor pressure of the water. In this case, if there are bubbles tends to like destroy your machine. Not it's not exactly to say that they destroy the machine, but they lower the level of efficiencies of your machine, so it's not able to work anymore. Alright, so let's try to see what happens in this case. You start from tank number A, you want to move from tank to number B, and your flow is given in this direction. So basically you start with a kind of level of energy, and then when you go till the pump from this point to this one, you are observe of course a decreasing of your energy. Then there is the pump increase your energy, and again you will have after the pump the decrease until the final level. So let's try to see. Again, we define the total head before the pump, and the total head after the pump. Let's observe that if y is equal to 0, which means that the total head of tank A and tank B are of course equal, you are in front of closed systems. And while if y is less than 0, you are in front of the gravity system with pumping station. So basically you can insert pump in two different situations for two different objectives. The first one is when you want to move, exactly as in this case, the flow from tank A to tank B, and in this case your flow doesn't have the necessary energy to make this movement, so you put the pump to increase the level of energy of your fluid. The second case is when, for example, you have that your fluid in tank A is at a higher energy level of the second one. So basically your flow can naturally go to tank number A to tank number B, but the fact of inserting a pump is related to the necessity of, for example, increasing the volumetric discharge that flows inside your systems. Alright, so again we have HM, which is the total head before the pump, and this will be the total head in A minus the distributed losses along pipe number 1, so J1, L1. In HV you will have again HB plus the kinetic height, so alpha that multiplies put 2 to the power of 2 over 2g, these terms, plus J2L2. Alright, so delta H, which is the energy, the increasing of energy due to the presence of the pump, will be, in this case, H. If we want that this will be higher than 0, it will be HV minus HM, which is Y plus the energy losses. So, again, let's try to see it in another way. Alright. Okay. So, we have tank 1, then we have the pipe, the pump, and the second pipe, and the tank number 2. Let's try again to use the same letters. So we have A and D. Alright, so we have right here L1 and L2. So what we get from the slide was, just after our consideration, was that delta H pumps are equal to the total head after the pumps minus the total head before the pumps, which were equal to Y, so Y again is HA minus HB plus the losses. Let's write now, trying to explain this thing, just applying Bernoulli's theorem from tank number A to tank number B. So, again, no concentrated losses, which means that we start from HA, then we see the first losses associated with J1, L1, then we have the increasing which are exactly delta HT, so it's plus delta H pump, sorry, delta H pump. Then again we have minus J2L2, so the distributed losses associated with the pump number 2, and everything, of course, we are, well, I'm not able, and I'm, okay, sorry, well, this is not good, this is the true line, so forget about this, because we are reaching the level, and I don't have anything to erase it, but anyway, and everything is equal to HB. So again, from this point, you link this point to the free surface level in tank B. Because you don't have right here, or better, we are not considering right now the concentrated losses at the exit of your pipe. Then again, if I want to get delta HP, I will have that delta HP is equal to HB minus HA plus G1L1 plus J2L2, but remember that HB minus HA in this case is what we have defined as Y. So in this case is YHB minus HA, in this case is greater than 0. Why? The fact that A was greater than B becomes Y minor than 0. So in this case we'll have HB minus HA, which is Y plus exactly the losses. So basically what I would like to say to you is that when you consider a pump or a turbine, you are considering something that it's increasing or taking a part of your energy. But that amount of energy must be positive. When you want to evaluate this amount of energy, this must be positive, because in the end, this amount of energy, it's necessary to evaluate the power, and the power is something that is always positive and not negative, of course. So the better things to remember, the only thing that I think that is really necessary to remember is that if you have a pump, you increase your energy. If you have a turbine, you decrease your energy right now. In the end, again, you can compute the power transferred to the fluid as the specific wave, gamma times Q, that multiplies the delta H, so the energy due to the pumps, and to evaluate the transfer power to the pump, you have to take this quantity and divide it by the efficiency of your pump, which is a value that usually ranges from 0.75 to 0.80. All right.